What if I told you the sun is exploding right now and has been for 4.6 billion years? That sounds like clickbait. It's not. The sun is a continuous thermonuclear explosion, and yet it doesn't blow itself apart. It doesn't burn out. It doesn't flicker like a giant candle in space. Instead, it shines with astonishing stability, delivering about 3.828 times 10 superscript 2 watts of power every single second. So why hasn't it run out of fuel? Here's where most people get it wrong. The sun is not burning like fire burns wood. Fire is a chemical reaction. If the sun were powered by chemistry, it would have died in a few thousand years. That's not speculation, that's physics. The total chemical energy available simply isn't enough to power billions of years of sunlight. So what's really happening? At the sun's core, temperatures reach about 15 million degrees Celsius. The pressure is so immense that hydrogen atoms, which normally repel each other, are forced together. When two hydrogen nuclei fuse, they eventually form helium. This process is called nuclear fusion. And here's the jaw-dropping part. Every second, the sun converts about 600 million tons of hydrogen into helium. Wait, that sounds like it should drain fast, right? But here's the twist. Out of those 600 million tons, about 596 million tons become helium. The remaining 4 million tons don't disappear. They're converted directly into energy through Einstein's equation, E equals mc squared. That tiny fraction of lost mass releases an enormous amount of energy because the speed of light squared is a gigantic number. That energy is what becomes sunlight. Still, if it's losing 4 million tons of mass every second, shouldn't the sun be shrinking rapidly? Surprisingly, no. The sun's total mass is about 2 times 10 superscript 3 kilograms. At its current rate of mass loss, including energy radiation and solar wind, which removes roughly 1.3 million tons per second, the sun is losing only a tiny fraction of its total mass over billions of years. It's like skimming a single drop from an ocean every second. Now here's the part that sounds almost controversial. The sun is not on fire, and it's not a chaotic explosion. It's balanced. Perfectly. Gravity is constantly pulling the sun's mass inward, trying to collapse it. At the same time, the energy from fusion creates outward pressure. These two forces counteract each other in a state called hydrostatic equilibrium. If fusion slowed down, gravity would compress the core, increasing temperature and pressure until fusion sped up again. If fusion sped up too much, the sun would expand slightly, cooling the core and slowing the reaction. It's a self-regulating system. That balance is why the sun has remained relatively stable for billions of years, and why life has had time to evolve on Earth. But here's another surprise. The sunlight we see today didn't leave the sun's core today. When fusion produces energy in the core, it starts as high-energy gamma radiation. That energy doesn't travel straight out. Instead, it bounces around inside the sun, being absorbed and re-emitted countless times by particles in a dense plasma. Scientists estimate it can take anywhere from 10,000 to 100,000 years for that energy to reach the surface. So the sunlight warming your skin today began its journey before human civilization even existed. Now let's confront another common fear. Will the sun suddenly burn out? No. And we know this because we understand stellar evolution. The sun is currently in what's called the main sequence phase of its life, the long, stable period where hydrogen fusion occurs in the core. Based on its mass and luminosity, scientists estimate the sun will remain in this phase for about 10 billion years total. Since it's about 4.6 billion years old, it has roughly 5 billion years left before major changes begin. That's not speculation. That's based on well-tested models of stellar physics, confirmed by observing millions of other stars at different stages of life. But here's where it gets dramatic. The sun won't burn out like a dying ember. Instead, when hydrogen in the core becomes depleted, the core will contract under gravity. That contraction will heat surrounding layers, causing hydrogen fusion to occur in a shell around the core. The outer layers of the sun will expand massively. It will become a red giant. At that stage, in about 5 billion years, the sun could expand far enough to engulf Mercury and Venus. Earth's fate is still studied in detail, but even if not swallowed, it would become uninhabitable long before that due to rising solar luminosity. Yes, the sun is gradually getting brighter. Since its formation, its luminosity has increased by roughly 30%. Even now, it brightens by about 1% every 100 million years. That slow increase will eventually trigger a runaway greenhouse effect on Earth, likely within 1 to 2 billion years, evaporating oceans long before the red giant phase. So the real story isn't that the sun might suddenly burn out. It's that it's slowly, predictably evolving. And here's another fascinating piece of evidence that confirms our understanding. Neutrinos. During fusion, the sun produces neutrinos, nearly massless particles that barely interact with matter. Trillions pass through your body every second without you noticing. Detectors on Earth, like the Super Chemio Candy in Japan and the Sudbury Neutrino Observatory in Canada, have measured these solar neutrinos. They match the predictions of nuclear fusion models. In other words, we're not guessing about what powers the sun. We're measuring it in real time. Now let's zoom out. The sun contains about 99.8% of all the mass in our solar system. Jupiter holds most of the rest. Everything else, planets, moons, asteroids, comets, and you, make up a tiny leftover fraction. Yet despite its enormous size and power, the sun is considered an average star. There are stars that burn hotter, live shorter lives, explode as supernovae, or collapse into black holes. Our sun is relatively calm, and that calmness is the reason we're here. If it were more massive, it would burn fuel faster and live only millions, not billions of years. Complex life might never have had time to evolve. If it were smaller, it might be cooler and lock planets into tidal positions that challenge habitability. So when we ask, why doesn't the sun burn out? We're really asking a deeper question about balance, physics, and cosmic timing. It doesn't burn out because it isn't powered by fragile chemistry. It's powered by nuclear fusion, an incredibly efficient process governed by gravity and quantum mechanics, stabilized by equilibrium, confirmed by neutrinos, and sustained by an almost unimaginable reservoir of hydrogen. But here's the final twist. The sun is actually converting only a tiny portion of its total hydrogen supply. Fusion happens only in the core, which makes up about 10% of the sun's mass. That's the region hot and dense enough for sustained fusion. So even though it sounds like it's consuming 600 million tons per second, it's doing so from an enormous central reservoir. And it's doing it steadily. Right now, as you're listening, 4 million tons of matter just turned into pure energy. Again, and again, and again. So the next time someone says the sun is burning, you'll know that's not quite true. It's fusing. It's balancing gravity against radiation. It's converting mass into energy with cosmic precision. And it has about 5 billion years left before the real fireworks begin. If you're fascinated by the physics that keeps stars alive and shapes our universe, follow for more deep dives into the science that most people never stop to question. And now I want to ask you, if the sun has been stable for billions of years, what do you think is the most fragile balance keeping life on Earth possible right now?